So hello everyone, welcome to the P1 program. This lecture is called P108.3 and in this lecture we are going to look at three different aspects of applications of Newton's law. So the first aspect is gravitation. So we will understand what gravity is and Newton's law of gravitation, and then the other thing is Coulomb's law, right? This is something that is different from gravitation and all other things, but this has something to do with forces. That's why I'm introducing this, and we will discuss more about this in the second program, which is P2 program for electrodynamics and electrostatics. So we will do that when we get there. So for now we are going to do this, and then afterwards I will do some comparison, and then later on I will explain constraint forces, right? So constraint forces, what they are, and we are going to look at them. So generally this is a force review, right? So and also we will look at what the total force acting on a system are. So let's begin. So the first thing that we need to do is gravitation. So Newton was the one who proposed gravity. So gravity is, as you all know, something that attracts a massive body towards the other massive body. So if you have two massive body, then they are both attracted, right? So that's the essence of gravity. So if you are sitting on the surface of earth, then an apple falling down is because of gravitational pull of earth onto that apple, right? So that's how simple as it is. So that's called gravitational attraction, basic gravitational attraction. Now in modern terms, gravitation is defined as a little bit different. Okay, you have something like a massive body of say mass m1. M1 massive body is going to cause some ripple in the space-time fabric, and that ripple will also be there for another mass, say m2, right? M2 mass, and there will be another ripple, and these ripples interact with each other, and you get a common attraction, right? So these bodies ripples interact with each other, and you get these two bodies to come closer and closer. So these m1 and m2 will become closer and come closer and closer because of the curvature in space time. So if you want to understand space time, well, we will discuss it afterwards, maybe in the portion where we can look into relativity. Maybe we will get as far as general relativity if time permits. Then at that stage I'll discuss this in much more detail. So for the time being, the space time curvature is a curvature in space where these band is represented by, this is the space, right? So this is the space band. okay so this is the space band, and whatever that is in this axis is called the time axis. So there is some dilation in the time axis, like the time axis is actually getting twisted and bent further, creating a ripple in the space, and that's the space-time curvature. okay so maybe this is something much more harder to imagine for you guys, but this is what actually is happening. So heavier objects will impose a heavier curvature on the space-time fabric, and more heavier objects like black holes create something that are curves which are almost extending down to infinity. So that's how space-time curvature looks like. So we will discuss the physics of this maybe in a later part of this course. For this time, this is the effect of the most modern interpretation of space-time fabric. Now that aside, okay every body attracts other bodies having mass to each other with some force, right? So that's the basic thing. A massive body attracts another body with some force. There is a force of interaction. So that force must be, so the force must be proportional to the mass of the two bodies, say m1 mass and m2 mass. So the mass of the two bodies and is also inversely proportional to the square of the distance by them, and that is called the force law of gravitational law of Newton. Okay, so this is for so far the most accurate representation of force acting between them. This is experimentally driven and proven. Now, so that force is proportional, that means the force can be made equal to, so force must be equal to the m1 m2 by r square times a constant. This constant is called g. So g is called universal gravitational constant. Okay, so g is the universal gravitational constant that's which complements for this proportionality. So what this means is that if you, okay, okay, you can use the equivalency principle now. Okay, equivalency principle states that any force will have the dimensions of m a, right? So which is a is a vector, f is a vector. So here this vector is r cap, so r is a vector here. So this equivalency principle states that, okay, so you know for a fact that a body under the influence of the gravitational force of earth, when it comes down, is going to accelerate at the acceleration of g, right? So g is the acceleration here. So you can say a is here g, so you can say mg must be equal to, in magnitude, must be equal to m1 m2 by r square g, right? So you can cancel this. M1 is the mass of the body that is falling down, so that's the mass of the body which is falling down. So this is also m1. So now you can say that g must be equal to, you can cancel m1 and m1 from both sides, and you get g must be equal to some m2 times g, capital G by r square, right? So what this gives you is that you know the value of g, right? You can experimentally measure the value of acceleration of a body under the influence of earth's gravity. Now that is 9.8 meter per second square, which is approximate. So now you can find out the value of g because you know the mass of earth, right? Mass of the earth, or m2, which is the mass of the earth, which is 5.9 times 10 to the power 24 kilograms, right? And the radius of the earth is 6378 kilometers, right? So those are known values. Now what you can do is that you can substitute those values into this equation of g, and you can find g must be equal to, so g must be equal to uh, small g times, which is acceleration due to gravity, times r square by m2. So now you substitute those values and you get g is equal to 6.672 times 10 to the power minus 11, right, meter cube, kilogram raised to minus 1, second raised to minus 2, or in a good fashion you can write down that it is Newton meter square per kilogram square, right? So that's g. So that's how you can estimate the value of g. So this gravitational constant is a universal constant, right? So the small g, the value of small g is innate for earth, right? So for the case of earth, you have the acceleration due to gravity, which is 9.8, but the gravitational constant g, which is 6.67 times 10 to the power minus 11, which is an absolute constant. So it is not going to change when you go from one part of the universe to the other part of the universe. So that's how you can estimate a universal constant out of measurements that involves only earth, right? So using the earth's measurements itself, we have found out a universal constant. So that's the achievement here. Now there is one more thing that is needed to be said, right? I cannot skip that. That is, if you are looking at earth here, right, it is rotating in an axis. Say this is axis here, so it is rotating like this. So that means that it will have some a gravitational pull onto itself in this direction. For any body that is standing here, right, if you are a guy standing here, then you will be pulled onto this gravitational force. But at the same time earth is rotating, right? So it's rotating in this direction. That means it is being pushed out by the centripetal force or centrifugal force, which we will discuss later on to the course. So the gravitational pull or push will be different at different parts of the earth's surface, right? At poles, the gravitational acceleration, which is maximum, because there is no little rotation on at the pole region. So at poles g is around 9.83 meter per second square, and at equator g is 9.878, okay, 9.78 meter per second square. So because of these rotatory motion, so that's also an information that I should tell you at this moment, because we are discussing it, right? We will go into detail later on to this course. Now something that I need to mention next is the Coulomb's law, right? So it's the Coulomb's law. So what does Coulomb's law has to do with this here is it is also a force, right? There are charged particles everywhere, and your running of the electricity in your home is based upon the existence of charged electrons which are moving around inside the conductor wire, which are moving around, positive and negative charges moving around and causing electrostatic force, right? Electrostatic force or electric current that is driving through these wires and causing all these mechanical effects that are running your tube lights or even your fans or even your air conditioning or TVs or anything like that. So basically everything is run under the influence of electricity in our modern times. So electric charges, the smallest individual charge that we can take out, right, a free charge that we can take out is an electron. So electron has a charge, right? Electron has a charge, E has a charge, you can call it E, which is equal to 1.6 times 10 to the power minus 19 coulomb, right? This is measurable. So coulomb is the unit of charge, okay. So that's the first thing. That means that's the amount of charge it has, right? So it's a unit measurement, it's a unit for measurement. Now what we can do is that these like charges, you see, two, there are protons and electrons, positive and negative, okay. So positive protons are there and there are electrons which are negative. So what happens in nature is that positive charges repel each other with each other and negative charges also repel with each other, but positive and negative charges attract each other. So like charges repel each other, so positive and negative will repel each other, and negative and positive or positive and negative will attract each other, right? Attract each other. So that's a natural occurring phenomena, right? So these attraction and repulsion was measured by Coulomb, right? Coulomb experimentally measured this attraction and repulsion, and he found out that this force in nature is proportional to the product of charges, which is q1 times q2. Let's call it q1 and q2, two charges, and it is inversely proportional to r square, which is as similar as the force of gravity, where you can see it is proportional to m1 and m2 and is inversely proportional to r square. So it is similar, these are similar forces, and that's why similar looking forces, and this is natural forces, that's why I have mentioned this here, okay. So q1 f is proportionality is with q1 and q2 divided by r square. So he Coulomb formed out a fundamental law that says F must be equal to some constant times q1 q2 by r square. So the direction here is in the r cap direction. This is also in the radial direction, and similarly the gravitational force is always acting in radial direction. Okay, so this force is a vector, that's why there is a direction involved. Now he found out, Coulomb found out, this constant k has a value of 9 times um, 9 times 10 to the power 10 to the power 9. Okay, 10 to the power 9, that's the value of this constant, right? So you can find out the unit of this constant. It will be Newton meter square per what Coulomb square, right? So that is going to be the unit of this constant k. Anyways, now that's how Coulomb found out this relationship between charges and the forces acting between them. Okay, now what we are going to do is that this is a topic of electrostatics which we will handle when we go to the P2 program, where P2 electrodynamics, and when we discuss that we will go in much detail about these charge distributions and uh, different aspects of charge like field and all that. Okay, so now for this purpose, now what I'm going to do is that I'm going to assume that there is uh, two electron, right? There is two electron. Okay, one electron here which is having a negative charge, and another electron here which is also having a negative charge, and they are separated by 1 meter distance. Okay, so that's what I'm assuming. Okay, if that's the case, then what I can do is that I can find out the gravitational force, right? Fg, which is g g times m of two particles, which is mass of electron. Two of them are the same, so mass of electron the whole square by distance, that is 1 meter square, so that is 1. So that will be, you can substitute the value 6.67 times 10 to the power minus 11 times 9.1 into 10 to the power minus 31, which is the mass of the electron square, divided by 1. So that will give you the value of 553.56 times 10 to the power minus 73 Newton. Okay, that's the force that you can directly find out, right? So this is the gravitational force or between two electric charges, right, of masses of electron, two electric charges. Without looking at the charge distribution, the based upon the mass itself, there is gravitational force, right? This is the gravitational force, let's call this one. Okay, this is Fg, gravitational force. Now let's find out what the electric force is, right? So F electric will be 9 times 10 to the power 9, right? That is k times C1 C2, which are both the same, which is 1.6 times 10 to the power minus 19 the whole square, at C1 C2 the whole square, divided by, or q1 q2 the whole square, divided by distance square, which is 1, again 1. So you get a result of 2.3 times 10 to the power minus 28 newtons. So that's the force of electric force, right? So this is the electrostatic force of two particles, two electrons sitting here, right? So two electrons are sitting here with 1 meter distance apart, and there is force of gravity between them, and there is force of electrostatic attraction or Coulomb's attraction between these two particles. So that's how experimentally you calculate them, right? So if you see this, I call it as equation number 2. Okay, so if you look at number 1, which is the gravitational force, I am approximating it to be equal to 10 raised to minus 73, because it's such a small number, and this will be approximated as 10 to the power minus 28, right? So the ratio, if you can imagine, the ratio between electrostatic force and gravitational force is around approximately around 10 to the power 43, right? 10 to the power 43. So what does this mean is that, okay, what does this mean is that electrostatic force of attraction or repulsion is 10 to the power 43 times bigger than gravitational force. So anywhere you go out in the universe, right, if you go out into any part of the universe, electrostatic forces will be much bigger than gravitational forces, right? Then I'm going to ask you a question: why is earth not being affected by electrostatic force, but it is being affected by gravitational force? And you can see earth rotating around the sun, it is rotating around the galaxies, the planets are rotating around under the influence of gravity, and we don't measure the effect of electrostatic forces, right? In real life, when you throw a ball, right, throw a ball to one place to another, you measure gravitational pull and forces, but not electrostatic forces. The reason is the average gravitational electrostatic charge present inside, or electric current present inside flowing through, or electric charge present inside any material is negligent compared to mass. So mass will be much greater for real things, for almost everything around in our earth will be much bigger than the charge present inside. Okay, so that's basically the reason why charges are much more important when you go to smaller scale, as of the scale of electron or something like that. Okay, when you are dealing with something that's so small, then electric charges are much more important than mass, right? So that's the end of the comparison. Now what I'm going to do is that I'm going to introduce constraint forces, right? So there is something called constraint forces in nature. So what is a constraint force? So the technical definition here is that if you have a body, say you have a thread, and you are putting a ring around it, a small ring, so this ring is supposed to move in either direction, so it cannot move in any other direction. Okay, so that's a constraint, right? That's a restriction. So the motion that is possible is in two directions, and whatever the forces are in, right, it will act on these two directions. So that's a constraint acting force. Now if you similarly, if you are restricting yourself inside a gas chamber, there is some gas molecules present inside. These gases are restricted to be moved within these boundaries of this gas container. You cannot go out from that. Okay, that's a restriction, and that's a definition of constraint force. Now the other thing I need to do is that you have something like the contact force, right? So it's a contact force. So what is a contact force? Let's imagine that you are pushing this is a table here. Okay, this is a table here, and you with your hand are pushing on to this table with your hand, right? Are pushing onto this table. It's not a very good hand, anyways, you have to adjust with that. You're pushing onto this table downwards. Okay, so you're pushing downwards here, and what happens is that these at the point of contact on the table, you will find that the force is being applied, and your hand is being pushed back, right? So the hand is being pushed back by the table, and you apply some force downwards. So at the point of contact, there is something called the contact force, right? The contact force acts backwards. So this is the axis here, and the contact force will act on to your hand backwards. So the contact force, you can say, the contact force which is acting on the surface will be looking like this, and contact force will have a perpendicular force and C parallel, right? So this parallel component and perpendicular component are interesting, right? C perpendicular is called normal force, and C parallel is called frictional force. So those are two forces. C perpendicular is called a normal and C parallel is called a frictional force. You see that normal forces, when you apply a force, you can clearly understand that what is a normal force, what is a and what is actually a frictional force. Okay, so if you look at this in a different way, you can see that, so the if you are looking at this, right, so the at the point of contact, the force normal is in the up direction and the frictional is in this direction. The other force, which is the gravitational pull of your hand, will be in the downwards direction, right? So that force is mg, right? So you can see that these perpendicular force must be balancing this mg, right? So the perpendicular force must be balancing this mg, so you can say this must be equal to this mg. So the normal force must be equal to mg, right? So because it has to balance the downward force, right? If the idea behind this is that if you are on a table and you put your hand on there or a box on there, then if there is a downward force and there is an upside force, here it is called normal force, here this is gravitational force, then these box mustn't move, right? It shouldn't move if the forces are cancelling each other, right? So your hand is actually on the table and it doesn't move. Okay, it's always on the table. So that means these forces are being balanced. Which means normal force is equal to gravitational force, or you can say normal force is equal to mg. So that's easy way of understanding it. Okay, now what I'm going to do is that this force here is, there is something called the friction, right? So the frictional force, if you want to understand that, so your hand here, I'm going to redraw the hand anyways. Okay, so this is your hand, this is your hand, somewhat your hand anyways. So if you push on a box or a board or a table, you can see the contact force acts on this direction, backward direction, right? It will push your hand back when you push down onto the table. So this contact force, we resolved it as two components, and this contact force, what you cannot do is that you cannot go down, right? So you are restricted to go down because the table is pushing you back. So that's why normal force must be equal to mg. Okay, that's the reason why. And the second thing is that you cannot slide your hand when you're pushing, because there is something that is restricting you from sliding your hand, and that force is pushing you back, right? So that force is called the frictional force. So frictional force, it's a bit tricky. If you look at the frictional force, you have a rigid surface and you put a box onto it, right? So this box is 1 kilogram, right? So you have the normal force here and complementing the gravity, and what you cannot do now is that you cannot go in this direction or in this direction, because there is friction, right? There is friction. Okay, now if you put down something different, which is on a surface, you put down, say, a feather. Okay, it's not actually a very good feather, so I'm going to redraw this anyway. Okay, so I'm going to draw the surface here. Okay, this is the surface, and on another color I'll, okay, this is a feather. Okay, you have to adjust with it. Okay, this is a feather. So if this is a feather, you can see that this feather is actually having some mass. It will have a normal force which must be equal to the gravitational pull, and this feather is not supposed to move in this direction as well, right? It will have the same force. But what different is here is that the weight of the feather is much smaller, right? So the normal force is much smaller. Okay, and then as the weight is much smaller, the frictional force must be smaller, right? So somehow the frictional force must be proportional to the weight. right? So frictional force is proportional to the weight. So if the weight is higher, the frictional force is higher. So the weight is actually equal to the normal force, right? We have did that. So frictional force in fact must be proportional to the mass or the normal force, right? Normal force. So you can say frictional force must be proportional to here. Okay, I didn't write. Okay, proportional to. So a frictional force must be equal to some constant. I'm calling it mu s times normal force, right? So that's frictional force. Now this is a technical definition of frictional force. So heavier the object, right? Heavier the object, heavier will be the frictional, higher will be the frictional force, right? So, and this is the definition you can derive from that, right? This is the old proportionality definition. So frictional force must be equal to, so you can so forth and you can say that frictional force frictional force must be equal to mu s times m times g, right, which is normal force. So now you see that there is no component of area or anything like that, right, in this equation of friction. So that means that friction is independent of area or anything like that. It only depends on the mass of the body, right? It's weight of the body. It only has direct dependence on the weight of the body and the type of surface it is sitting on, right? No other thing is depending upon that. So heavier the object, higher will be the frictional force, right? So that is called the frictional force. Now if you want a diagram, right, force diagram, which is something that we have an object here on the surface of a table, and there are charges inside. There is charge inside, positive negative charges, all those things. And what are the forces involved in this thing, right? So you can first of all see that there is this gravitational force, F gravity, which is equal to mg, and there will be normal force upwards, right? So that is equal to mg as well, right, in magnitude. And then there will be electrostatic force between these electrons and protons present inside, electric charges present inside, so there will be that force. And then there will be frictional force due to the surface, which is F friction on either sides, and it will be equal to mu s times normal force, which is equal to mu s times mg. So that's the force which we have discussed. Now these are the forces, elementary forces. Now if you take the axis, which is all the up and bottom, up side will be taken as positive, a coordinate system, and downside will be taken as negative, and to the right you take it positive, and to the left you take it negative. You can see that mg normal force here, so normal force is positive and mg is negative, so gravitational force, which is negative, and it will cancel each other, plus the electrostatic force or Coulomb force Fc is there, which is should be positive depending upon it is right or left, which is another intricate detail. And the frictional force is on either sides, so frictional forces will cancel each other if it is at rest, and if it is moving in either directions, if it is moving to this direction, right, the friction will be in the opposite direction, right? So if this body is moving in this direction, the friction will be in the opposite direction, right? For a body moving in this direction, friction will act in this direction, so it will be negative. Or if the body is going to move here, then the friction will be in this opposite direction, so it will be positive. So that's how the frictional role is going to play. So there is normal force, there is gravitational force, there is frictional force, and there is Coulomb force, right? So these all will have signs as well. Okay, signs as well. So these are the total forces acting on a body. And whenever you are asked to decode a system, to understand a system, you are supposed to find out the exact forces acting on this body, right? The total forces acting on the body you have to find out, right? So that's the objective here. Okay, total force. Okay, so if you do that, you can solve the problem, and you can find out the resultant force and how much faster. So this total force must be equal to ma according to equivalence principle. So you can find the acceleration of the body if you know the total force. Okay, so that's, and I'm going to stop it right there, and we will discuss about tension in the next lecture. And all the best for you guys.